Well, I tried to make this one interesting. We're going to evaluate the following line integral for each parametrization of the parabolic curve. And does the result seem logical? Well, we'll have to go back and wait till we get a result before we know if that's true. So our vector field f of xy is y times I plus x squared times j. Our curve r1 of t, if you look carefully, 4 minus ti, 4t minus t squared j, t going from 0 to 3. Let's see, if t goes from 0 to 3, then we're going from 4i to 1i, and this is going from 0 to, let me see, we got 3, we got 12 minus 9, 0 to 3i. I'm sorry, I said 0 to 3i. I should have said 0 to 3j. So in other words, our R1 is this blue thing going from here to here. That's our, we're going to evaluate the integral over this four field of this vector valued function. And so, for R1 prime, that's pretty easy to tell, negative 1i, and then 4 minus 2tj, right? And therefore our f of x of t, y of t is going to be, well, this is x and this is y. So, and our f is yi, well, that means 4t minus t squared I, and plus x squared j, and x is 4 minus t, so it's going to be 4 minus t, the quantity squared, j. And the line integral we would set up is the dot product of this vector that we just found and our r prime, which we found at about the same time. So that's what we're going to, now don't forget the result of a dot product of vectors is a scalar. And of course the limits 0 to 3, they come from the way our vector valued function is described, or maybe the way our vector valued function describes curve C, right? And so the dot product, let me see, that would give us this times negative 1, so that makes it, actually you could call that t squared minus 4t is another way of looking at it. And then this 4 minus t, the quantity squared, times 4 minus 2t, well, there that is. And algebraically, I won't bore you with the details of that, but it's awfully easy to multiply that out, so I'm not going to bore you with that. I'll just say I was able to use my software to quickly go from here to here, and while I'm at it, since that's just polynomial integration, and you should know how to do that without a hitch, and so that turns out to be 69 halves. Okay. Now, it got more interesting. Remember, say, what have we used R2, this curve? And I want you to notice R2, if we started out at 1, that would be going from 1i and 3j, so from here along till when t is 4, that would be 4i, and this would be 0j. So, and trust me, I didn't do it, but if you solved, let's say, spent some time deciding what this vector value function looked like, if x equals 4 minus t, substituting, well, you could solve that for t and find x, and then put the, in terms of t, and put that value in here, we would get a value for y that would show it to be this same parabola, okay? Just trust me on that one. It would take a little bit of extra time that I don't want to take, but trust me that this is the same curve. Only, well, one thing is different about it, we're going in this direction this time though, huh? But the vector field remains unchanged. So what do you think, without calculating it, what do you think is going to happen when we go in the opposite direction on that same curve, even though it's described a little differently, because remember this was 0 to 3 and that one's 1 to 4. So what do you think is going to happen when we do that? Well, let's see. For this path we have r prime is 1. I'll tell you what I'll do, just because I might need to do this so you can understand why that's the case. I'll bring this back down here where we want it to be. See, r2 prime is 1i, and then 4 minus 2tj, And our f of x of t, y of t, well, remember, oh, you know what, I better bring that down too. So bear with me a second. Oh, went back too far. Here's our force field, vector field. So now, okay, now we want to replace our x, sorry, our I component with y. Well, that's this. So that's 4t minus t squared. And we want to replace our j component with x squared. Well, that would be t squared. So there it is. That's our force field. And the line integral would be the dot product of our r2 prime and our force field. There it is. And again, the dot product's pretty easy. 1 times 4t minus t squared plus t squared times 4 minus 2t. See that? And like I say, I won't bore you with multiplying that out. And then when we integrate, it's only polynomial integration. But look what we get as a result, just what you expected. We got the same numerical answer as when we went in the other direction, but this time instead of positive 69 halves, it's negative 69 halves, and I'm sure you would have expected that. Okay, the change in direction, all it did was alter the sign, but the absolute value of the line integral was the same. And think about it, if we were calculating the work needed to push a rocket out of Earth's gravitational field and compare that to the work required to slow the rocket down to stop its descent, the work would be the negative of the work it is to launch it. Of course, coming back to Earth will require some sort of retrofying rocket, and the problem is similar to the one above, though. The descents are not controlled in this way in reality. Parachutes or controlled flight in the space shuttle is now that part of the round trip. And so it's done, actually with the shuttle it's done differently. The shuttle actually can fly, sort of. But if you think about it, you know, moving in one direction and the other, all it does is negate the work. There are lots of things in physics that are that way. For instance, if you throw a ball up into the air and it returns to Earth, it hits the speed with the same speed, it hits the Earth with the same speed you threw it up in, right? So there's lots of things like that. Of course, it would be a negative speed, but it's really basically the same principle.